name is Shashank Shekhar. So today we will talk about actinoids. Okay. So we have already studied lanthanoids. So if you just remember, the lanthanoids are present in one of the two panels that are present at the bottom of the periodic table. And in lanthanoid, the 4f orbital is filled progressively. Right. So if I talk about actinoids, then in actinoids, the 5f orbital are filled progressively. So and about the position, so they are present at the bottom end. So at the end of the periodic table, the period is called as what? The period is called as actinoids. So we have 14 elements again in actinoids, starting from TH to LR. Okay, that is thorium to lawrencium. So this is the positioning of actinoids. Now let us talk more about actinoids. So the actinoids are radioactive elements, and due to this reason, not much is known about these actinoids, and the earlier members have relatively long half-lives. So what is the meaning of this half-life? So basically, if you remember, then all of the first order reaction, all of the radioactive reaction are what? They are all, say, first order reaction. Okay. Now, due to this reason, we cannot calculate the full life because this reaction ends at infinity. For that reason, we calculate the half-life. And the one which is having a longer half-life means it is comparatively more radioactively stable. Okay, or there is more nuclear stability in that element. Now, if we talk about the earlier members, means if we are having a smaller atomic number in case of actinoids, means they are more nuclear. There is more nuclear stability in that element, whereas the latter one have half-lives ranging from a day to 3 minutes. So lawrencium lasts up to 3 minutes only. Okay, it means in 3 minutes, half of the lawrencium is converted to what? Is radioactively decayed. So you can see how fast it is decaying. Now the latter member can be prepared only in nanogram quantity. Due to the radioactive property, it can be only prepared in the nanogram quantity, means a small amount. All the actinoids have a configuration of 7s2 and a varying number of electrons in the 5f and 6d. So we have seen this, right? So in case of lanthanoid, we have the 6s2, whereas the 5f and 6d have varied number of electrons. Similarly, in case of actinoids, we have 7s2 as a constant, whereas the 5f and 6d electrons, the number of electrons in the 5f and 6d are changing. So 14 electrons are added to 5f orbit F subcell, excluding thorium. Now the 5f orbital are completely filled at element 103, that is lawrencium, which has F14 configuration. The variation in the electronic configuration are due to stability of F0, F7, and F14, means half filled, zero filled, and full filled. Due to this, we see the exception. So the configuration of americium and cerium is 5f7 and 7s2, whereas for curium, it is 5s7 and 6d1. Means one electron that is present, it is not going to what? It is not going to 5f, or it is not getting paired up with the electrons that are present in 5f. Instead, it is going to 6d. Now the 5f orbital resembles the 4f orbital but are not as deeply buried, which enables them to engage in more bonding. Clear? So what does it mean? It means this line means that the electronic behavior of the, say, lanthanoid and actinoids valence electrons are same, but since 5f orbital are present more outside, or they are not that much penetrated as compared to 4f, so this helps them to engage in bonding. Now the general trend in lanthanoid is observed in actinoid also. This is gradual decrease in size of ions or M3 plus ions across the series, means we must have remembered that on moving from left to right, the atomic radii of the lanthanoid were not that much significantly decreasing, but they were decreasing. Similarly, their ionic size are also decreasing. So this can also be seen for the what? This can also be seen for our actinoids. Okay. So this is the important part. If you see here, for actinium, we have the general case. Thorium, we have the general case. But protactinium has a exception because it has F2 configuration and 61. Again, F3 configuration and 61. F4 61. But as we move to plutonium, then it has 5F6 and 60. Moving on to americium, it is 5F7, right? Curium has 5F7, 61. Again, they are only means F is only field. If in case of berkelium, californium, einsteinium, fermium, mendelevium, and nobelium. So all these have only F orbital field. The D orbital is not disturbed. The disturbance is seen for this 4. Okay, that is this 3. That is neptunium, uranium, and protactinium. For curium also there is an exception, but it can be easily explained with the help of half filled and full filled concept. But this is not seen in case of proactinium. Okay, although we have 61, okay, 61 here. If I talk about the oxidation state, then again the common oxidation state of actinoids is also +3. Okay, you can see that in the extreme ends, they have +3 oxidation state. +4, +5, +6, +7 can also be seen. But again, +3 is the most stable oxidation state. If I talk about the electronic configuration of M3+, then it is F0, 1, 2, 3, 4, 5, 6, going up to 14. If I talk about the M4+ configuration, then it starts from 5F0 and goes to 5F13. Clear? Okay. Now, it must be referred that actinoid can also go contraction. Similar to lanthanoid contraction, we have also actinoid contraction. Okay, we have also actinoid contraction. So this will be referred to as actinoid contraction, but the contraction is, however, greater from elements to elements in the series, resulting from poor shielding of high-wave orbital. So if I talk about the oxidation state, they have a greater range of oxidation state. +7 can also be seen, but it was not seen for the case of lanthanoid. And it is attributed to the fact that 5F, 6D, and 7S are of comparable energy. So these 3 are of comparable energy, and for that reason, removing an electron from either of these 3 is almost same. For that reason, we see a number of oxidation state. Now, in the first half of the series, a frequently element exhibits higher oxidation state. So if you just go back and see, you can see that the earlier member are exhibiting higher oxidation state, like neptunium is and plutonium is exhibiting oxidation state of +7. But as we move down, the number of oxidation state decreases. This is due to the greater nuclear charge. So as we're moving from left to right, the nuclear charge increases and it becomes difficult to remove the electron. Clear? Now, the actinoid resembled lanthanoid in having more compounds in +3 oxidation state rather than +4. But +3 and +4, they tend to hydrolyze. Means if you just react it with water, they tend to hydrolyze. The distribution of oxidation state is uneven and different for the former and latter elements. So former have variable oxidation state, while the latter have only +3 oxidation state, and it is unsatisfactory to review their chemistry in terms of oxidation state. Now, actinoids metals are silvery. Again, similar to our lanthanoid, they are also silvery in appearance. Okay, but display a variety of structure due to irregularities in metallic radii. High reactivity metal, especially finely divided. So if they are finely divided, then their activity increases. Boiling pointer gives oxide and hydride mixture, and it combined with non-metals at moderate temperature. So we'll see these reactions. What are these reactions? Hydrochloric acid attacks all nitric acid slightly affects due to protective oxide layer. Alkalis have no action on this. What? Actinoids. So magnetic properties are more complex than lanthanoids. Variation in magnetic susceptibility roughly parallels lanthanoids but lower value. Now 5 orbital penetrates less into inner core, so 5 orbital are more shielded from the nuclear charge. Okay, so you know it very well. So as the atomic number, the principal quantum number value decreases from 4F to 5F, 5F has a greater outward exposure. So because they are less penetrated, outer electrons are less firmly held and therefore they are available for bonding. Now, if we just compare comparison with lanthanoid, behave similar to lanthanoid, not evident until second half of the actinoid. So if you just see the second half of the actinoid, they are much more in resemblance with the lanthanoid because one property is common. You can see that they have +3 oxidation state on the latter side, but on the former side they have a variety of oxidation state. Early actinoids resembles lanthanoids in close similarities and gradual property variation without oxidation state change. Now, lanthanoid and actinoid contraction, they both have contraction due to involvement of f orbital, and due to which their size decreases more faster, right? Lanthanoid contraction is more important at chemistry element exceeding actinoid is less known. So what is the meaning of this? So if you just look at the periodic table, then after actinoids, the metals which are present, their chemistry is of not that much importance, whereas the lanthanoid contraction, after lanthanoid contraction, the metals that are being seen are of important use. So that is why lanthanoid contraction is of much importance. The D block elements occupy the middle section, and where the F block is progressively filled. So let us just summarize D and F block, right? So if I talk about the summary, then the D block elements are starting from group 3 to group 12, okay? Whereas the F block elements are on the downside, right? So transition metal are typically metal because they have properties like ductility, malleability, thermal and electrical conductivity, and their successive ionization enthalpy do not increase that much rapidly because of the presence of d orbital. Now the transition metal exhibit paramagnetic properties due to the presence of unpaired electron, and also they exhibit catalytic property due to variable oxidation state, and they form colored ion because of the DD transition. Also, they have interstitial property, means they can form interstitial compounds and alloys. The first series of the transition metal oxides are formed from reaction of metal with oxygen and dissolves in acid to give oxalometallic acids. Whereas the lanthanoid and actinoid constitute the F block, and the lanthanoid show a gradual decrease in atomic size. We have seen this. Now the lanthanoids are soft white metal which have a +3 oxidation state at the stable oxidation state. The D and F block elements and their compounds have various applications in steel, catalyst, complexes, organic synthesis and more. So this was for today's lecture. With this, I end my lecture. Thank you.